We've done derivatives of polynomials. Let's move up a little bit and talk about radical functions. So here's a nice y equals x to the power 1/2. Well, why'd I write it like that? I could have put y equals the square root of x. They're the same thing. So if I wanted to calculate the derivative of this function, once again, I can give this a name. I'll call it f1. And I'll say, Desmos, show me the graph of y equals d on dx f1. So remember that d on dx is our notation for the derivative. The x here is telling me the variable that I'm using for differentiation, and that becomes important as we work with functions whose variables are not necessarily x, though I'll save those for another lecture. I've written this as f equals the square root of x, and this is supposed to be the derivative of that, but there's not a reason I can't call this one f2 and say, tell me the derivative of f2. That's exactly the same thing. So what's going to happen is I actually find this notation with the exponent written out as a number more helpful, because we can still use the power rule. I have x to a power, so my derivative is going to be y equals, I'll take the old exponent and move it down as a coefficient. I'll have a 1/2. I need to take x and I'll raise it to the power of 1 less than the old power. So that'll be a half. Oops, that should be in the coefficient. That should be in the exponent. Work with me. There we go. 1/2 minus 1. So again, we have the same function, just arrived at two different ways. Or I could go ahead and say that this is a half of x to the negative 1/2 power. So the fact that this is rising off to infinity here in my derivative is reflective of the fact that my square root function actually has a very steep slope for small values of x. And then as the function grows, you can see that the slope is actually decreasing. That rate of change is slowing down. And we can detect that in the derivative because the derivative is getting smaller and smaller in magnitude. So this was a pretty straightforward group of functions to look at, and this will actually work for any radical, because once again they are just all different powers of x. I can write f1 equals, let's take a 4th root of x. This is x to the power 1/4. Let's have Desmos calculate that derivative. So show me the graph of the derivative of f1. There it is. And if I want to do it myself, I'll say y is equal to, the old exponent is a quarter, so a quarter comes down as my coefficient. I have an x. I'm going to raise that to the power of 1 less than 1/4. So a quarter minus 1 gives me minus 3/4. So any radical that we've got, I would first convert it so that I can express it as a power of x. And from there, I can go ahead and just use good old power rule, one of the easiest rules for differentiation. All right, I will see you in a bit.